Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is 2018 NDS and CLT design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Bastian Kuhn will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the webinar content for the next hour today, I want to start off in our main program, RFEM. So RFEM is what's going to allow us to model the basic geometry of our structure, and we'll also be able to fully load it. Then I'll move on to the add-on module concept with RF-Laminate in particular and how we interact that with the main program, RFEM. We'll take a look at the 2018 NDS CLT updates, in particular Chapter 10. Then we'll go back to our example and we'll launch RF-Laminate, and here's where we're going to define our CLT compositions, take a look at stiffness considerations, loading conditions, and serviceability, because we can give you deflection checks as well within the add-on module. And finally, we'll run a full analysis and design of the CLT structure according to the 2018 NDS. And with that said, we can immediately jump into our example today. So when you first launch RFEM, this is the dialog box you're essentially going to see. We need to give it a name. We can just call this one CLT10. The load combinations can be generated according to a standard. So you'll notice we have the ASCE 7 2016 here. We have the NBC 2015, as well as many other international codes. Now you can always uncheck this option here, and that will allow you to manually create your load combinations instead. So once we've defined that, we'll go ahead and use the ASCE 7 2016 for our example today. The program launches our file. So we can see in the center portion here is our main graphical window. This is where we'll begin to generate the structure. Down at the bottom, we do have our tables. If you prefer to work with the program this way, you can import and export information to and from Microsoft Excel. We have our tools up here at the top, and we'll certainly be utilizing those today. Over on the left, we have our project navigator. So as we begin to generate this model, all of our input data is going to be available within this project navigator. If we scroll down, here is a long list of all of our add-on modules. Here's RF-Laminate in particular for today. Now, once we do run an analysis, our results will be available within this project navigator. So to begin with, I want to start off again with just the basic geometry of our structure within the main program here, RFEM. So I'm going to draw a new line element, and it's exactly as you think. It's just a line element, something you'd see similar in AutoCAD. It doesn't have a cross section assigned. So what I'm going to do is to give the structure its basic outline here, and we're going to snap to a few different points. And finally, closing this gap, we can right-click, and we can also repeat the new line by right-clicking, and maybe I want to add an intermediate wall here. So once I'm done with that, you can see, again, nothing more than those one-dimensional line elements. Now, what I want to do to create the walls of this structure is to right-click on one of these lines, and we have the option to extrude the line into a surface. So this would be the 2D surface that makes up my wall element. Now, I can set the height as 9 feet. The thickness and the material don't matter right now. Steel A992 with a thickness of 8 inches is completely fine. The reason why, this is just essentially a placeholder. We're going to define our CLT compositions later on in the add-on module RF-Laminate. So as a placeholder, we can just leave these as they are. So now you'll notice that 1D line element was now created into a 2D surface element. The same thing can be done for the rest of these line elements to quickly create our walls. Now, by all means, you can draw the surfaces individually as well, which is what we'll go ahead and do for our ceiling elements here for our first level. So for this, I can just easily change my drawing grid up to the top of the structure. And I'm going to generate surfaces here. So this time I will draw in those surfaces. The material, again, doesn't matter. Steel A992, thickness doesn't matter. It's all going to be overwritten later. So I click OK. Now this allows me just to snap to a couple of points here. Now I wanted to place two panels side by side just to show you that panels don't necessarily need to span between certain walls, but they can be set up like this for situations where you are not able to span a single panel between walls. Now, as for our second room over here, I will just create a single surface element and we snap from one point to the other. So that is essentially defining all of the wall and surface floor elements for our first level. I'd like to go ahead and put in some openings here. So eventually we're going to create a second level. So I'm going to need some type of opening to get from the first level up to the second level with my stairs. So just like we drew in a surface, we can also draw an opening. So in our toolbar up here at the top, you'll notice that we have many different options for shapes of openings. It doesn't necessarily have to be a rectangle, but circles, semicircles, ellipses, or even a polygon to draw the shape yourself is available. So for this one, we will just use a typical rectangular shape, and we can go ahead and just snap to a couple of points here to add in that opening for our stairs. Now, as far as the front of the structure, we want to change around our drawing grid here and snap to the front. And we'll go ahead and add in an opening for our window to begin with, as well as maybe an opening for a door. So once those two openings are created, we'd like to do something similar to the back of the structure. Once again, just changing that drawing grid to the back, we rotate around the structure and just arbitrarily adding in a rectangular opening for the window. Lastly, we need a way to get in between the two rooms, so we'd like to add a door opening. So we'll go ahead and change around the drawing grid once more, snapping to that center point, and then we can add in our opening. So you'll notice the benefit of this drawing grid, that it really doesn't matter where I'm snapping to within the model to draw all these openings, but the drawing grid limits me to where those openings are actually placed on the structure. So all of the surfaces are pretty much done. And I'd like to generate a second level with basically the same identical layout. So what we can do is just to highlight everything, and we could use our Move Copy tool, but what's nice is we also have our drag and drop feature within the program. So with this, I highlight everything, I hold down my Control key, and then I can snap from one node up to the top to create a copy with that drag and drop. So now you can see everything was copied up to the second level. Now I do want to delete a couple of these openings. This is probably easiest by turning this into wireframe view. I can zoom in here, select my top opening, just hit the delete key. Now the nodes and lines still remain that made up that opening, and realistically you could leave these in here. They're not going to affect your analysis, but if you just like to keep the model a little bit more clean, we can just go ahead and select those with our selection tool and hit the delete on our keyboard. Same thing goes for our opening of our door. We probably don't need this one in here. So again, just highlighting and hitting delete on our keyboard. So we're now done with all of these surfaces for our simple building today. Now, let's say that we'd like to model some type of beam element that will hold up the two panels here. So this is a fairly long span of 15 feet. And just for example purposes, let me hide this second level here. So we'll change the visibility by hiding the selected objects. So where I want to place that beam is below these two panels that are spanning a little bit longer. So how can we do this? Well, we can start off by drawing a new single member. Now the member type is set to beam, and we can launch our cross-section database. So here are all of the different cross-sections available in the program. So you'll see all of the sections from the standards, AISC, CSA standards, but in particular today we'll be working with these parametric timber sections. So we can choose the rectangle, set the width as 6 inches and the depth as 10 inches. The material is also set within this same dialog box. Now, today I want to use a glue-lam member. So here I can import the material from my library. And over on the left, we have some filters. So we'd like to filter according to timber. We can choose North America. Here you'll see both the AWC and the CSA. Then we have our long list of all the materials directly from the NDS standard. So you can further filter according to the tables directly from the back of the NDS. For example, glue laminated softwood timber, stressed primarily in bending. We choose that from table 5A. Well, now our list is a little bit smaller. You can always create favorites groups, which is just a way to add a handful of materials to a favorites group. And that way you can quickly access them rather than having to change these filters and sift through these materials every time. So for example, I added my material today to my favorites group that I'll be using within the webinar. So here are all my material properties for that particular selection, and I choose OK. So now we click OK through our dialog boxes, and it's as easy as choosing a point to snap on our structure. Now again, the program has nice AutoCAD-like features. So the point that is perpendicular to my opposite node will automatically be highlighted, and these are called O-snap settings. Again, something you'd see similar in AutoCAD. So our beam element was created here. Now, a couple of considerations. We probably don't want to transfer moment from this beam to our plates and vice versa. That would probably cause too much torsion within this beam, and realistically, the connection will most likely be screws from the panel down into this beam. So how can we release that moment? Well, what we can do is to utilize something called a line release. So turning this into wireframe view, let me just break apart this member here so that member is now still spanning as a continuous member, but I broke it up into 2 segments where each panel occurs. To add in a new line release, we can either do that within our project navigator over here. You can see line release types, or we can choose it under the insert model data, and then you'll see line release types down here. So utilizing the project navigator, we right click and choose new line release. Now the program asks us to select the line, so I can choose my first initial line here. Then we choose the line release type. So I create a new type, and you'll see here we have translation, but this is where we want to release that rotation. Now, these axes, X, Y, and Z, are based on the local axes of the line. It is not the local axes of the beam element, and it's not the local axes of the panel, but rather the line that they share itself. So we can select the option to completely release that rotation. The program also asks us, well, what is the released object? So we can select this surface on the far end and click OK. So now you'll see this line release symbol shown within the model. If I right click, I can repeat that same line release, this time choosing the other line. My line release type was already defined, and we'll choose our surface closer to us, and I click OK, and now I'll see that line release to release that rotation between the 2 surfaces and that beam. The other thing to take a look at is we most likely want to drop this beam element below our surfaces. We want to account for that eccentricity because it is holding up the beam element or the panels itself. So for this, we can easily select both members for the beam. I double click it, and here is the Options tab. Now the Options tab has member eccentricity, and I create a new definition type. So what I could do is to manually define, okay, what is half the thickness of my panel, what is half the depth of my beam, and to manually put in that eccentricity. But rather, the program's smart enough to do all of that automatically for us. So what we can choose here is the top of the beam member point, and we can offset it from the bottom of the surface. And I just graphically select one of these surfaces, I choose the bottom, and I click OK. So now we can see visually that beam dropped below that panel. So what's nice here is that eventually we're going to change these steel panels to CLT. Well, our thickness is inevitably going to change too. So instead of having to come back here and adjust the eccentricity, the program will automatically update everything for us. Okay, so the basic geometry is now complete. The last thing we need to do before loading the structure is to support it. At the bottom of my walls, I'd like to add in line supports. So once again, with our tools up here at the top, I can choose New Line Support. We have two default options, hinged or rigid, but we can always create a new line support ourselves. Here you'll see the 6 degrees of freedom, 3 degrees in translation, 3 in rotation. We have the option for partial fixity. So if you have something that's not fully fixed, not totally released, but somewhere in between, then you'd probably want to add in here a spring constant. And lastly, nonlinearities. Nonlinearities can be extremely useful for wood panels and CLT panels here. The reason why is that maybe we want to have a full, in compression, we would like the wall to bear down on the foundation. But with any uplift, well, maybe we'd like the release of those force transfers, and instead we'd like to model in there some hold downs. So that's where those nonlinearities would come into play. Today, we'll just be utilizing a simple hinged line support, and we can select all of our lines at the bottom of the structure. Now, one thing we want to do is to select the two line supports where our door openings are and delete those. The reason why, the program will give us an error just saying that we're trying to support something that really doesn't exist, so we'll just preemptively take care of that. So geometry and supporting of the structure is done, so we can move into the basic loads. For this, I'm going to go into a new load case. So here pops up my Edit Load Cases and Combinations dialog box. The first load case we're going to define is dead load. The action category is set to dead load. This is important because this is how the program knows which load factors to assign according to the ASCE 7 2016 that we selected at the beginning of the model. The self-weight is automatically activated for dead load. We create a second load case. We'll call this one live. The action category is set to live. Self-weight is unchecked here. We don't want to account for it twice. Third load case, we'll call this one Wind X with the action category set to wind. And finally, our last load case will be Wind Y with the action category again set to wind. So the combination expressions tab is just going to show me that I'm going to create both LRFD and ASD load combinations, again, directly from the ASCE 7. The load combinations tab actually lists out the individual combinations. So here are my LRFD load combinations in orange and ASD in red. Now these only include the load cases that I've defined on that first tab, which is dead load, live load, wind load. I won't see additional load cases such as snow load when I haven't defined them on that first tab. The result combination is an envelope solution. So we have our LRFD envelope solution here for our first result combination and ASD result combination here. This will just show us the max and min out of all of these load combinations combined. So we've completely set up our load cases and our load combinations, but we need to actually place the loads on the structure. So we'll start off with dead load, and here we'll just apply a basic surface load, once again accessing this tool at the top of our model. And the surface load direction will be set in the global Z direction. We can see those global axes here with the magnitude set at negative 0.1 kips per square foot. For this, I can just click on those surfaces, or I can highlight the first level here to apply that same load. Now you'll notice that the openings are automatically considered and our dead load is complete. Same thing for live load, same concept. We'll go back to our surface loads here and we'll just simply change the magnitude to negative 0.05 kips per square foot, and we'll only apply this to this first level here. Moving on to wind load, under Tools, Generate Loads, for both snow loads and wind loads, we do have the option to generate these according to the ASCE 7 2016. The wind loads only take into consideration case 1 and case 3 from the standard. And realistically, this is for basic rectangular structures only. Anything outside of that, you're going to have to manually apply the loads. And this will apply them as either surface loads or member loads to the external elements of the structure. So it won't be placed on a diaphragm as a nodal load, but rather the actual loads themselves. Just keeping with a simple example today, we're going to apply basic surface loads for our wind in the X and Y. So going back to our surface load, all we're doing here is changing the load direction, and the magnitude can be set at 30 pounds per square foot. Now, you can vary the load linearly in the vertical direction. For example, if we want higher wind load at the top, lower wind load at the bottom. And these loads don't necessarily have to be applied to the entire surface either. We have free loads, which allow you to apply surface loads to only portions of your surfaces. So the possibilities are really endless when it comes to loading here. So we just apply a basic wind load in the X direction. Now, I'd like to maybe have a small suction load on the other side. We'll just simply change the magnitude to something more like 10 pounds per square foot and apply that on the other side of our structure. So pretty basic application today. Moving on to wind in the Y direction, same concept, just changing the load direction to Y and the magnitude to 30 pounds per square foot. We click on these front surfaces here. Again, you'll notice that the windows and door openings are automatically accounted for. And one more time, a small suction load in the back, 10 pounds per square foot, and we can always highlight all of these surfaces at once to apply it to the back side of our surface. So that's the basic loading. Now we can cycle through these load combinations here to see them all applied at once. What's also nice is that these load factors are automatically considered in the graphical interface here when we're displaying the loads on the structure. Okay, so you would think that, all right, we must be already ready to run our analysis, but remember, we still have steel surfaces here. We haven't even touched the definition of our CLT panels. So this is where we want to launch the add-on module, RF-Laminate. And again, I can access this add-on module within my project navigator here, and we double click it, and up pops a dialog box. So the add-on modules are nothing more than a dialog box within RFEM. Everything that I've already modeled and loaded so far will be considered. I don't need to redefine any of that information. The only thing that I'm defining here is information specific to the NDS standard and to cross-laminated timber. So I want to fill out a few things here before I explain what's going on with the RF-Laminate add-on module concept. So the first thing we'll choose here is design. You'll see the NDS 2015, and as of our last release, we added the NDS 2018. We have both ASD and LRFD. Maybe today we utilize LRFD. Our surfaces, we can choose all the surfaces here. So you could select some graphically if you only wanted to design a few, but for today, we're going to design all of them. Our ultimate limit state combinations, we will choose all of our LRFD load combinations, and serviceability, we will choose ASD because, again, we can check deflections. So the material characteristics, so this is where we define the CLT compositions, those individual layers that make up that CLT panel. And this is where I want to go back to the PowerPoint here to explain what's going on behind the scenes. So with RF-Laminate, as I just mentioned, we're going to define each individual layer of that panel. Now, each panel has its own stiffness matrix. So what the program will automatically do for us once we have filled in all of the layers, it will generate an overall stiffness matrix. And you can see a sample calculation here, D11 of that stiffness matrix based on all of the layers that we've entered in. It will export this global stiffness matrix back out to RFEM, and this is where we're going to see CLT panels instead of those steel surfaces that were our placeholder. It's going to run through all of those load cases, load combinations, and eventually we're going to get internal forces. These internal forces for our CLT panels are going to be brought back into RF-Laminate, where the stresses are distributed to each individual layer. So maybe a cross-section profile here of a CLT panel for bending stress might look something similar to this. And finally, we're going to separate those stresses into tension, compression, bending, and shear components. We're going to compare them to our strengths of our CLT based on the NDS standard, and we're going to give you a design ratio. So that's essentially what's happening underneath the hood. Now, as far as the 2018 NDS updates, what exactly changed? And In reality, there were only 2 revisions in Chapter 10 for CLT. The first being the format conversion factor K sub F, and this is applicable for the rolling shear design value F sub S within LRFD design. Now, within the 2015, this was 2.88, and it was simply adjusted to 2.0. You can see this within Table 10.3.1 of the 2018 standard, and within RF-Laminate, when you have the 2018 selected, will automatically take into account that small change. As far as the second change, it actually is a little bit more complex. So deflection calculations are run according to Section 10.4.1. And what the NDS code tells us is that the apparent bending stiffness must be adjusted to account for shear deformation, and this is what you're seeing over here with this equation. So in order to calculate deflections, we should use this stiffness. And this is pretty much an approximate equation, and it's done by reducing the bending stiffness EI with a shear deformation adjustment factor K sub S. So we can see all of that here. So this equation was slightly modified, and it matches up a little bit more closely to the CLT handbook, but that's really the only second change. Now, with all of that said, RFEM, or any structural analysis finite element software, really has a hard time knowing what this shear deformation adjustment factor should be. First of all, it's based on the end fixity of our panels, whether it's pinned or fixed, and the loading. So the program doesn't know this criteria. There's no way to determine this. And what happens when we're outside of some of these elements, like the end fixity is partially fixed, or the loading doesn't necessarily have any one of these in particular, but multiple loading options. So what K sub S value do we use then? So instead, what RF-Laminate does is it will calculate the effective shear stiffness, and this is D44 and D55 within the global stiffness matrix that I just mentioned for each panel according to laminate theory. So this effective shear stiffness will be used for the deflection calculations, which take into account both shear and bending deformation. So we take a little bit more of an exact approach. Therefore, this change within the NDS really doesn't affect us today with RF-Laminate. Okay, so let's jump back to our example here, and let's begin by defining our first composition. So what we'll first define here are our floor panels. So we give this current composition a name. We choose these surfaces, which we can choose them graphically here. We'll choose our roof level and our first floor level, and I click OK. Now, as far as the different layers, you can individually choose these layers here by going into our material database, and this is what we saw similar in RFEM. The material category can be set to Wood North America. We have AWC and CSA here, and then we can choose one of these materials that's applicable for our first layer. So that's one way to do it. We can set the thickness, and then all of these properties will be generated automatically from that particular material. But another option is just to bring in the imported layers from our library. So within this library, you'll see here that we have a handful of producers that we have reached out to. They gave us their information for their products that they've created for CLT. In particular, for the Canadian and US market, you will see here the APA. We'll see here Nordic Structures, StructureLam, and SmartLam. So you can always import one of these products directly from the manufacturer if you are utilizing one of them. Who we'll be utilizing today is the APA. For the US, grade E2 is fine, and we will select the thickness as 6 7/8. So now you can see that all of these layers were automatically populated within this dialog box. Now, if you create your own individual layers, you can always save them and bring them up for a future model within RFEM. So a lot of options here. You don't necessarily need to individually define those every time. The modulus of elasticity, shear modulus, specific weight, and everything, again, is automatically populated here. And this is based on the producer that we're utilizing. The material strengths, again, everything is automatically populated here. So here are strengths for bending, tension, compression, and shear strengths. So that is good for the floor, but we also need to create a second composition for our walls. So we'll call this one walls. These surfaces, we can graphically select all of our vertical panels here for our walls. And we go back to the add-on module. We populate from this same database here, and I'm just going to use the same grade E2, 6 and 7/8. That's fine for our case today. And I click OK. So one thing I'd like to point out is this option here to edit the composition details. Now this is applicable for both the floors and the walls, and there are quite a few options here to turn on or off or adjust. You'll notice we have consider coupling, we have cross-laminated timber without glue at the narrow sides, we have shear failure in the glued contact surfaces, as well as stiffness reduction factors. So to explain all of this, although it looks pretty simple, it's actually fairly complex what's going on once again in the background of RF-Laminate. So I'm going to jump back to the PowerPoint to explain some of these settings, and they're incredibly important as us as engineers because we need to input in the right information in order to get a correct analysis. So the first option, consider coupling. This is automatically turned on by default. And the reason why is we're going to make the assumption that these layers are glued to each other at both the top and bottom. So you can see here the stress diagram when we are considering coupling. So here are normal stresses as well as shear stresses and the stress distribution that we're seeing for coupling behavior. Now in turn, with no coupling, we now have really independent behavior for each individual layer. You can see how this stress distribution looks quite different. So that's why we make the assumption you probably want those layers glued, but if not, you can always uncheck this to consider the coupling. Now the second option, without glue at the narrow side. So this is a pretty exaggerated picture here, but for each one of these layers, it's comprised of plank elements. You know, maybe these planks are 3 inches wide, 5 inches wide, whatever. So with these planks, they potentially could not be glued at the narrow sides. And like I said, this is an exaggerated picture, but this is what's going on. So when you have this option checked, we'll automatically set the modulus of elasticity in the local Y direction of the panel to 0. We're going to assume that you have no stiffness in that direction. Now, with that said, those stiffness reduction factors also need to be adjusted. So that will take us to our next slide. So without glue at the narrow sides, it is strongly recommended that your K33 and K88 stiffness reduction factors be modified. So this is for torsional stiffness, K33, and K88 is for our in-plane stiffness. Now, what's interesting is that the NDS and the CLT handbook really don't give much information on how these should be reduced when we don't have glue at the narrow sides. So what I did is I went ahead and pulled this information from the Austrian Annex, which is the Eurocode EC5. And I think we all can admit that Europe is a little bit more advanced when it comes to CLT design simply because it's been around a lot longer than what we've seen within the US or within Canada. So I think it's perfectly fine to refer to the Eurocode when there's portions in the NDS or CSA that maybe aren't so complete. So within the Austrian Annex, we have some simple equations here for K33, K88, those stiffness reduction factors. And this is an Excel file I got from one of my colleagues. And what this allows us to do is just to simply put in the total thickness of our panel, the number of layers, the board width, and then out pops these calculations for K33. So this is the value we want to put back into RF-Laminate when we are not considering glue at the narrow sides. Same thing goes for K88 here. So by default, these are set to 1.0 even when you have this option checked, and that's simply because there isn't any guidance given to us within the NDS standard. So again, though, it's strongly recommended to make sure you reduce those stiffnesses. Okay, so as far as the other two stiffnesses, K44 and K55, I want to briefly touch on this. These are actually not stiffnesses you'll probably be adjusting. And the reason why is that the CLT shear stiffness is calculated according to the laminate theory. And I actually just mentioned this with our deflection checks that were new within the 2018 NDS. So with this, we're going to apply a shear correction coefficient. And in turn, the CLT handbook actually actually utilizes the shear analogy method. This is different than the laminate method. Both of them eventually come up with a reduced shear stiffness, and that's ultimately what matters. So either one, by theory is probably considered fine, but within RF laminate, we're going to use the laminate theory. Here we're going to apply the shear correction coefficient to our shear stiffness, G and A. Now, when we're looking at a homogeneous rectangular section, it's pretty common to set this shear correction coefficient to 0.8. We can see the shear stress distribution as a parabolic type function. Well, with CLT, we don't have that parabolic type function because it's not a homogeneous section. Therefore, through research, there are some recommendations on what to use for that shear correction coefficient, whether it's 3, 5, 7, 9 layers. We have some ranges here to set that to. But the question is, okay, well, if I have 5 layers, like my example today, what exactly do I set this factor to within this range? Either the low end, the high end. What happens if I have 11 layers? What do I use then? So we will actually take you to the next slide to show you how these shear stiffness calculations for in the XZ and YZ directions are calculated according to general technical regulations. So here are the equations for the shear correction coefficient. And we can see how that shear correction coefficient comes into play when calculating the D44 and the D55 stiffness matrix entries within the CLT panel. Now, within RF laminate, here are the complex equations that go into calculating D44 and D55. So this is how the module is calculating those stiffnesses. Now, this is all within our help manual within RF laminate, so you do have access to all these equations and the theory behind the module. But point being that I will show you in just a minute how you get the values of these D44 and D55, and you can back calculate to eventually come up with what the shear correction coefficient actually is for that particular panel. So all of that is done though automatically, and so this is why I say you rarely will need to adjust the shear adjustment factors for K44 and K5 because it's already being done underneath the hood. Finally, the last option that we have here is shear failure in glued contact surface. So this is for a new torsion check, and this was just added into the program within our last release. And this is mainly for wall elements which are loaded in plane. I think we can imagine with gravity loads and wall elements how maybe torsion could potentially be a concern. So it's considered without glue at the narrow sides again. And one suggestion here is to make sure that we set our FE mesh within our model to approximately the same size as our board or our plank widths. And so we'll be doing that a little bit later on in our example, but again, it's important because your results could be a little bit skewed if you choose an FE mesh too small or too big. So just something to keep in mind. Now, this verification once again comes from the Eurocode EC5 2010 version. The NDS, the CLT handbook don't mention torsion, and they don't go into detail about how to take that into consideration. So we have pulled these complete interaction equations from the EC5, which you can see here. So the torsion checks have essentially 3 elements here, 3 different terms, and I've broken these terms down into these equations over on the right-hand side. So what we can do is to activate the shear failure. And by the way, you'll also want to turn on your results for now the torsion checks. These interaction equation results will now be displayed in RF laminate, but we have to manually turn those on. They're still going to be calculated. It's just you can see how many options here you can view with your results in the laminate module. We don't want to overwhelm you. So we'll be sure to do that as well. Okay, so we're finally ready to jump back to our example, and here we are back to that original dialog box. So I'd like to set the plank widths to 4 inches, and again, for my walls, I want to reduce that stiffness to 0.49 for my torsion, and for my in-plane stiffness, 0.59, and that was all just based on the PowerPoint that I just went over, and I click OK. So now for my walls, I've only made those changes to the walls. My floors, which we can pull up in here, remain unchanged. I'm not applying those stiffness reductions. But for each individual layer, I can view its stiffness matrix here. And just like what I mentioned, the program is automatically creating my global stiffness matrix here for the entire panel. So here's my D44, my D55 entries that I mentioned. You can eventually back calculate to see what that shear correction coefficient is. But everything is done underneath the hood, taking into account those adjustment factors. As I mentioned too, we want to actually, let's take a look at the material strengths here. Because we're now taking into account torsion, we will see a torsion strength added to our material strengths table. Now, this is something maybe you want to get from the manufacturer. This is just some arbitrary value. So it's not something that came from the manufacturers that we populated from these layers, because we don't have that information, but rather it's something that you need to manually fill in. Everything else should be good to go. Finally, under the details button, this is where I said you may want to activate the results for torsion. If we're checking for it, we want to see what that design ratio is. So turn those on, and those will be seen in the results. So finally, moving on down our list, we have our load duration. This is for load duration factors directly from the NDS standard. We have in-service conditions. Is our panel dry? Is it wet? What's the temperature? And finally, serviceability. So we can check deflections for these CLT panels as well. So what I can do here is I'm probably most interested in my roof panels and my first floor panels for my deflection checks. I click OK. The reference length, well, what is this referring to? Under the standard button, we see here serviceability limits. And this is our limiting deflection ratio. L over 360 is used for simply supported, and we have L over 180 for cantilevers. By all means, you can adjust these. These are just default values. So this is the L that we're referring to here. Now, either you can use the minimum boundary line of the surface, the maximum, or some user-defined length. Today, we can just use the maximum, for example, of 15 feet. So we're almost ready to run the calculation, but there's a couple more things that we need to take care of. So jumping back to the material characteristics, this is my wall composition, and we have 5 layers. Now, the orthotropic direction here is in reference to the local x-axes of my panels. So I have layers 1, 3, and 5, which are oriented 0 degrees from my local x-axis. This is most certainly the strong axis of my panel. I probably want to make sure that the panels are oriented with the local x-axis in the vertical direction to take those gravity loads. Otherwise, we're not getting as full use as we could be out of those panels if we orient it so that our strong axis is in the horizontal direction. So how do we check this? Well, we can go back into RFEM, and the first thing to notice here is that our panels are no longer purple for steel, but rather we double click on them. They're now considered with the stiffness laminate, and we can see the material is now set to RF-Laminate. So I can right click on any one of these surfaces to display the local axes, and I zoom in here. Well, the local x-axis is exactly what we don't want it to be. The strong orientation is facing horizontal right now. We want to rotate that 90 degrees so that that strong orientation of the panel can take those gravity loads. So how do I quickly rotate around all these panels? Well, for this, I can select all of my wall surfaces here, and I can double click on them. We have a tab called Axes. What this allows me to do is to change all of my local x-axes parallel to a line that I just simply choose in the model. So it's any arbitrary line, and maybe I choose this one in the center because it runs from the bottom to the top. I choose it, I click OK. I click OK once again, and now all of my panels are facing in the vertical direction with the local x-axes. So the strong orientation is now taking on those gravity loads. So incredibly important in terms of which orientation our panels are facing. The other thing, which I'm sure many of you are probably thinking of right now, is that we currently have fully fixed connections between all of these CLT panels. Well, we all know with CLT that this is definitely not the case. Rather, we're going to screw these panels in together. And with screws, we want to release the moment. We also maybe want to account for some slip of the screws, maybe at this location in the vertical direction, we have some movement. So how do we account for the CLT connection from one panel to the next? Well, we'll do this with something called a line hinge. Now, a line hinge, which can be accessed here in our project navigator, or again, we can access it here under model data, insert line hinges assigned to lines graphically. Now, line hinges are similar to our line releases, which remember we applied line releases to our member, but they're also different. We're actually going to modify the FE mesh elements at this location of the line hinge. So meaning if we want to release the moment, we're going to set the stiffness of the FE mesh at that particular point to something very, very, very small so that we're not going to see the bending moment. Whereas a line release is exactly what it sounds like. It's completely releasing and not adjusting the stiffness of the FE mesh. So as far as the line hinge definition, looks similar to a line release. We want to fully release the moment here. Again, these are based on the local axes of our line element, not of the panels. We also want to account for some slip. So this is along the local x axes of our line element, and we can put in here a spring constant of 50 kips per square foot. So now we're going to get some movement along the line length here, and I click OK. I'm going to choose the option to select the surfaces and have the program automatically assign the lines. I think that this is quickest. So I'm just going to make a selection here of some of my panels, and I'm being a little selective, and it will make sense why I'm doing so in just a minute. So I click OK, and we apply those line hinges. We can now see the line hinge symbol within the program. So when I zoom in here to the line hinge location of these two panels, what I see is both hinges on either side. Now, with any finite element software, whether it's RFEM or anything else, we know that if we have two beam members framing in at a joint, and those are the only two beam members that exist, and we set the end rotation of these beams to be released for moment, we're going to get an instability. You never want to set both beams in that case to pin. You want to leave one at least fully fixed. Otherwise, we get instabilities and we can have issues within the program. Well, the same thing goes for panels. At these locations, we want to have at least one fully fixed panel. So this is why I can hold down my control key to select some of these line hinges, hit delete on my keyboard, and as we see, we only have one line hinge defined at that joint. So same thing goes for the other side. We select some of these locations where we have too many line hinges defined, and up at the top, same thing. Otherwise, we want to avoid those instabilities. So holding down my control key, I'm just deleting some of them, and finally over here on the right hand side. So that takes care of the roof element, but we also want to select our second level here. We'll hide the visibility of that level, and we want to make sure that we address the line hinges at this ceiling level here. We'll just go ahead and select them graphically, because otherwise we have too many line hinges defined. Hit delete, and one more time on the far end here. Okay, so now we have completely finished the geometry of this structure. Loading, we've defined our CLT panels, so we're finally ready to run the analysis. Now, actually, one more thing I forgot. Remember within the PowerPoint, I said that we should really set the FE mesh for torsion when we're doing torsion checks approximately equal to the plank width for each individual CLT layer. So for my wall elements, I need to adjust my FE mesh. We do have FE mesh refinements in the program, so I can individually change each wall panel's FE mesh. FE mesh refinements are also available for line elements, nodes, anything of the sort. But rather, instead, under Calculate FE Mesh Settings, we can just change the global FE mesh, which by default is set at 1, to something more like 4 inches, because that's the size, the width of my planks. We can regenerate the FE mesh just to see how it looks, and the program does everything automatically for us. So everything's tying into nodes, to openings, to panels, to line releases automatically. If we make any changes, the program will automatically do this every time we run a calculation. So quite powerful when it comes to finite element capabilities. So now we truly are ready to run the analysis, and we can go back into RF-Laminate if we'd like to run the calculation here. Now, because I have slimmed down the FE mesh a little bit, this actually does take just a minute to run. So I wanted to jump to an already saved model here where we can launch RF-Laminate. And this will take just a second to load all of the results. So it doesn't take too long. It just takes a minute. You can see here it's having trouble pulling up all the results, but eventually, here we are. We're presented with the results within RF-Laminate. So after you run the calculation, you're going to see your results tabs available here, results tables. We can view the max stress ratio by loading. We can view it by surface. We can view it by composition. So maybe if we take a look at the results by surface, and I drag down my table down here, you'll notice that everything is synced up in the background. And what the program's doing is it's actually highlighting the surface that I'm currently looking at in the table. And it also has this big red arrow. That red arrow is showing me exactly where the controlling internal forces for that stress check are located. In addition, we can view this table here for surface number 4. We can view bending stresses. We can view tension and compression. We can view the shear. Here is the stress distribution throughout the cross-section of our CLT panel. And finally, you'll notice here that we have torsion checks as well for all of our wall elements. So for any one of these, we can scroll through and see the details of the stresses. Now, we're ultimately getting a max ratio check here of 0.74. We have a nice green smiley face because he's telling me that, okay, everything passes with all of these CLT panels according to the NDS standard, and we're below 1.0. We can always export any of this information directly to Microsoft Excel if we'd like to further sort it. Now, this is all included within the printout report as well. So taking a look at the rest of the tables, the max displacements, again, we're also doing a deflection check. We can remember this. So here are my deflections based on the analysis from the load combinations I've selected. Here is my limiting deflection, which remember that's for my limiting deflection ratio, L/360 is what I set it over. So my limiting deflection is 0.5 inches. Again, we get a different deflection ratio check here, 0.7, again below 1.0, so we're seeing our green happy face. And lastly, we see a parts list, which is nothing more than a material takeoff. Again, you can export this information to Excel. So these tables are very informational. Again, under the details tab, this is where you can turn on and off some of the different stresses maybe that you're interested in. But it's also nice to see our information graphically as well. So for this, we can always jump to the graphics view here. And technically, I'm still within the RF-Laminate add-on module, but I'm viewing my results graphically within RFEM. So what this allows me to do is you'll see here all of my load combinations that I've solved for, both LRFD and AST load combinations. So we can easily jump to any one of these load combinations within our project navigator here. Now, the composition, we can either choose our floors to easily view this, or we can choose our walls here. And in addition to that, we can view the 5 different layers. So remember, we have 5 layers that compose these CLT panels, so we can view the stresses within each individual layer. And even more so, we can view the top, middle, and bottom of each layer. So very, very detailed when it comes to all of the information that we provide you within the results for RF-Laminate. Then even more so, here are all my stresses available to me. We have bending stresses. We have some higher bending stresses where our openings are. This makes sense. We can view tension and compression, shear, and so on. And then all of our ratios will be available for these walls, fairly low ratios. Now, keep in mind for any of these checks here, we can always adjust our panel by double clicking on it, and maybe we're interested in any ratios that are 0.4 and lower. We can fill this in, we click OK, and then automatically the programs, we're actually still even lower than this, automatically the program will adjust those ratios based on our new panel here. This one actually might be a better example. We can change these stresses here. Maybe we're just interested in not quite 9.6, that's a little too high, but maybe we want 4.0. We choose the fill button, we click OK, and now we can see how that panel was adjusted here. All this information can be printed out directly to the printout report. You can choose mass printing, so that way we can print off all of these load combinations at once, for example, the bending stresses, added to the printout report, and then you can print that off either as a PDF or to your printer. So that's essentially CLT design within the program, including RFEM, the main program, and the add-on module. So we can go ahead and jump to our PowerPoint to conclude today's presentation. I know that was quite a bit of information. If you want to read more about RF-Laminate, RFEM, or any of our add-on modules, you can always visit our website at Dlubal.com. I always encourage everyone to follow us on our social media sites. For example, YouTube channel has all of our previously recorded webinars. On our website, you can find information like events and conferences that we'll be attending, as well as technical articles and so on. Our email at our Philadelphia office is info-us@dlubal.com. And our phone number here in Philadelphia is 267-702-2815. If you have any questions about today's presentation or anything else, feel free to reach out to us here. So many of you are wanting, or actually let me back up. So we will have many more upcoming webinars for PDH credit. You can always register at Dlubal.com under support and learning webinars. As many of you know, I sent out a couple reminder emails as well. So many of you will want PDH credit for today's presentation. That's great. Just a couple of requirements. Number one, that you were here for the full 60 minutes. And number two, you need to send me a request at info-us@Dlubal.com. That's info-us@Dlubal.com. So that's our email address. Just send me a quick email. Let me know you were in attendance today. If you had any other colleagues that were present, that's fine, and I'll be happy to issue that certificate. And with that said, I want to thank everyone for attending, and as always, we hope to see you at the next webinar. Thank you.